Yeah, so I think we can start the lecture now. My voice would be audible, I think.
Yes, sir.
Yes, sir. You are.
Okay, great. So in the previous lecture, we had covered some of the manufacturing process that are being followed in this IC design process, and we understood the basic flow of the IC fabrication process. And then we also understood some of the basic operations on the IC fabrication, that is few operations like oxidation, diffusion, etching, ion implantation, then chemical vapor deposition. So some of these basic operations, important operations, we also understood them. And then we also understood the importance of layout, and then how the layouts are transferred into mask, and then how the information on mask is transferred to the wafer via this photolithography process. And then we also understood how the MOSFET photolithography or MOSFET fabrication process is done. So what is the process behind the MOSFET fabrication? We understood that. And then we also talked about the CMOS fabrication process. Okay? And we saw what is NVEL and how the two devices, that is PMOS and NMOS, are fabricated on a single wafer. Right? So here is again the same basic flow for IC fabrication. So you start here with a substrate or wafer. You have a processed wafer, so crystalline wafer you have, and then on that wafer you perform these basic operations like diffusion, oxidation, photomasking or photolithography, ion implantation to create the diffusion regions, and maybe thin film deposition for metal, metal layer or some other layer, polysilicon layer, or maybe in the photoresist layer deposition also. Then after you have followed these operations on the on the wafer, you will have a finished wafer, and which you will put into the probe test, and then after testing you will perform chip separation. That is, you will separate these individual dies or individual chips by cutting them into slices, and then after separating them you will perform a visual inspection. Yeah? So visual inspection is performed to identify if there is some damaged chip during the slicing process, so that damaged chip can be removed. So it is not further processed. So only good chips are processed further. So after visual inspection, one can think about packaging the individual dies or individual ICs. So packaging or encapsulation, that is, you pack them or encapsulate them in some sort of hard casing or housing or protective housing like this, right? And then once you have this, one has to perform final testing, testing all combinations of input if possible, to see whether the integrated circuit behaves as required. So before selling to the customer, final testing is very important. Okay? My voice is clear, I think.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So final testing has to be performed. It is the most important step. So before selling it to the customer, one has to perform the final testing. Testing of the chip is very necessary. Otherwise, after selling it to the customer, if some errors or something comes up, and then the company will also lose its reputation, and also maybe it will lose its business in future, right? So these things, to avoid these things, complete thorough final testing has to be performed before selling it to the customer. Now let us talk about this layout and design rules, because we understand that the layout is the most important first step, and without layout one cannot think about manufacturing an IC, at least in today's era where the complexity levels are too high, right? So the first input is, that is layout. You need to understand how to draw the layout. And for drawing the layout, there are certain layout design rules. So while drawing the layout, one has to follow those design rules, and one should not arbitrarily draw the layout. But yes, there are some design rules. Again, these design rules are given by the foundry, that is the fabrication unit which will fabricate your IC. So they have their separate layout design rules. In fact, most of the foundries, they have almost common design rules. So these design rules have to be followed for making the layout. So what are these design rules and how to draw the layout? So that is what is the purpose of today's lecture. We'll understand what are those design rules and how to draw the layout using those design rules. Now, in a CMOS, technology, we understand, the today's complexity levels are too high. That is, number of devices can reach, from billions to maybe 1 trillion devices you will find, or more than that also, in a microprocessor. So obviously, for every transistor, one has to draw the layout of the transistor, right? And the layouts are nothing, as I said, that layouts are simply patterns of rectangular shapes. Yes, for example, these are the rectangular shapes, and they may represent the layout of your IC. So layouts are patterns of these sort of rectangular shapes, and the color of these patterns. So that also has a meaning. That is, if it is red color, so we normally say that it is polysilicon. Yeah, polysilicon line or polysilicon gate or polysilicon wire is red in color. Then similarly, P diffusion area and N diffusion areas. So they are, for example, P diffusion area is orange color, N diffusion area is green color. Metal one is blue color. So similarly, all other portions of your IC, that is, maybe your transistor has many layers. So a few of these layers have been mentioned here. That is P diffusion, N diffusion, metal, poly. So IC design process is a layered process. So layer by layer, it is manufactured. So one has to, let us say, first of all, deposit this P diffusion layer or maybe N diffusion layer, then maybe active layer, then poly layer, then metal layer, right? So it's a layered process. And since we have trillions of MOSFETs in IC, so obviously somebody will have to draw the layout of all these trillions of MOSFETs, right? Now, it would be easier if we say that the transistors are of same size. Yeah. So if transistors are of same size, so one would say, okay, I'll draw only one layout of one transistor, and then I'll copy the same layout of one transistor trillions of times, right? So 1 trillion time I'll copy the same transistor. Why would I draw, separate transistors each time? I'll draw one transistor and then I'll copy the same transistor trillions of times. So that is okay, permitted, provided the dimensions of the transistor remain same, right? So normally in the digital IC design or maybe any integrated circuit design, the dimensions of the transistor, that is width of the transistor, especially changes to optimize the performance of the integrated circuit. So always the width of the transistor can be varied to meet the performance metrics or to optimize the performance of the circuit. But let us say that the transistors even have the same dimension. All transistors are, let us say, have same dimension. Yeah, though this is not an ideal case, it will never happen. But let us say, for the time being, that all the transistors are of same dimension. So that means I will just draw the layout of one transistor and copy it 1 trillion times. Okay. But you will also admit that each transistor has 4 terminals. That is source terminal, drain terminal, gate, and bulk terminal. And let us say gate and source are, bulk and source are shorted. So let us say we have 3 terminals only now, right? So 3 terminals are in one device, right? And we have trillions of devices. So that means we will have to connect all these 3 terminals of 1 trillion device. So that means total 3 trillion connections we have to provide. That means wiring 3 trillion connections we have to connect via wiring, right? Either by polysilicon or by metal one line. So that is actually a very tedious task, right? And also time taking. Now, whenever we draw the layout or whenever we are designing the IC layout, so it is said always that one has to measure twice, okay, and fab once. Okay, so this is a very important line because you see that IC fabrication is a very costly business. Okay, so if your layout has some problems, you have not followed the design rules, let us say. Okay, there are some design rule violations and you did not clear those design rule violations. You did not follow the industry's guidelines, that is foundry's guidelines. Maybe let us say, metal one, let's say this is metal one, and it had some minimum width design rules. Right? So let us say that minimum width was supposed to be 2 micrometer, but somehow I made a mistake and I kept it 1.5 micrometer, right? And I sent the same design to the foundry. So foundry also did not check, let us say, and they fabricated a IC which has a metal line of 1.5 micrometer. Okay, or maybe some other violations are there, okay, because we didn't measure properly while designing the IC layout. Right? Now, what will happen to the final IC is, final fabricated IC is that it may not meet the same characteristics or same performance as were seen in the simulations. So that is, maybe it may not be completely functional at all also, right? So the entire IC fabrication process was a failure. That means, it was a huge loss of money, huge loss of money were there, right? Because of this mistake. That is, we did not measure properly while designing the layout. That is, you were not careful. Okay. So that is why it is said, because since it's a costly business, so measure twice, okay, and fab once. Okay. So this is very important. Okay. Now these measurements, so this is also important to understand these measurements. So today I think the dimensions are in nanometers. Yeah, all dimensions are in nanometers. Maybe the channel length is also in nanometer, then oxide thickness is also in nanometer, source and drain diffusion regions also you may find it either nanometer or micrometer. So one has to measure all these things and then draw the layout, right? So somebody has to draw the source and drain diffusion regions. So again, one has to measure what is the width of this diffusion region, right? What is the depth? Okay, depth will be controlled by, let us say, the ion implantation process, but yes, width can be controlled. Okay. Similarly, the oxide thickness, okay, channel length. So all has to be measured and then drawn. Okay. So these measurements obviously will be in either nanometers or micrometers. So it would be very difficult to measure in nanometers and micrometers, right? So we never, draw these patterns, that is, which define the layout. We never draw the layout by measuring the exact dimension, that is in micrometers or nanometers. We never do that. So what we do, there is another set of rules which are given by the industry, and those rules are called scalable rules or lambda rules. Okay. So what does that mean is, so lambda is actually a dimensional unit which is usually half of the minimum feature size. Okay. So instead of drawing in micrometer or nanometer, we say that the minimum feature size, that is channel length. Okay. So channel length, that is L. Okay. So we relate this 2 lambda to be equal to the channel length. Right. So this is a very important relation, and this sets a foundation for these scalable design rules or lambda rules. That is, you have scaled your channel length, which was, let's say, channel length was 2 micrometer. Okay, so you have scaled this 2 micrometer in terms of lambda. You are now representing L, that is 2 micrometer, in terms of lambda. Okay. So you will not, normally we will not draw by measuring in terms of micrometers or nanometers. We will simply draw in terms of lambda. Okay. So here, if 2 lambda is equal to L, so lambda is equal to L by 2, right? So that means if L is 2 micrometers, so lambda becomes 1 micrometer. Okay. So somebody says me to draw, a wire width of 1 micrometer. So somebody asked me to draw a wire of width of 1 micrometer. So I'll not measure 1 micrometer and then draw, okay, because it is a very tedious task. So what we will do is we'll measure or we'll draw in terms of lambda. I'll say that I have drawn a wire of width lambda. So what is this lambda in the layout editor which I will provide you? So let me come to this point here. So let us say that in the layout editor window, maybe this layout editor window, let's say it looks like this. Okay, and this entire layout design window is divided into grids of these kind. Yeah? So these dots are called grids. Okay, so the entire layout design window is divided into these grids. Okay, so let me draw these grids. Right, so these dots are called grids. Okay, now between, spacing between these two grids. Okay, so the spacing between these two grids, or maybe these three grids. So what is that spacing? Let's say we start from here and we end here. So this spacing is 2 lambda. Okay. And 2 lambda is equal to the minimum feature size, that is channel length. We had already commented. And let us say if L was 2 micrometer, okay, so lambda is equal to 1 micrometer. So that means each spacing between the grid is equal to 1 micrometer. That is, this spacing is now 1 micrometer. Okay, I'll say that this spacing is 1 micrometer. Okay, that means this 2 lambda is 2 micrometer. So this spacing between the two grids is 1 micrometer. Okay. Now somebody asked me to draw a wire now of width 1 micrometer. Let's say somebody asked me to draw a wire of width 1 micrometer and length is equal to 2 micrometer. Okay. So how will I draw? I will simply connect these two, let us say, grid lines. So I'll say this is width, and now the length is 2 micrometer. I'll connect and then I will draw it here. Right. So this is a wire of width 1 micrometer and length across this has 2 micrometers. Okay. So I didn't measure in terms of micrometers. I simply measured in terms of lambda. That is, this is lambda and this dimension is 2 lambda. I didn't measure in terms of micrometers or nanometers. So this has made the life of designer, somewhat simpler. Otherwise, one would have to measure in terms of micrometers or nanometer. It would have been a very difficult task, right? So these scalable design rules are for helping the designer, and these design rules are given by the foundry. Okay, the foundry or the fabrication unit, which will fabricate your integrated circuit. Okay, so lambda is usually half of the minimum feature size, and minimum feature size is the channel length of the MOSFET. So always somebody says what is minimum feature size? So minimum feature size is always the channel length. That is the minimum possible dimension you can draw in your IC fabrication process, right? Now, one of the scalable rules are given by this foundry called Moses, right? So Moses is one of the foundry which fabricates these ICs, and this fabrication unit Moses has given lambda design rules for designing ICs, IC layouts, and these rules are called Scalable CMOS rules, SCMOS. Yeah, Moses is a foundry. And they have given Scalable CMOS design rules, that is lambda rules. Okay. Similarly, we have another foundry. The foundry's name is Orbit. Okay. So you will find that in the simulation tool that I will provide you, the student version copy of the simulation tool. So there you will find two foundries are mentioned. One is Moses and the other one is Orbit. And both Orbit and Moses Foundries, they have given their own set of rules for designing a layout. So let's say for 2 micrometer or 1 micrometer technology, so they have given their rules. So one has to select those rules for extracting the parameters from the layout. So I'll tell you how to select that. But yes, let us digest that at this moment, that Moses and Orbit are the two foundries which have provided you this is scalable design rules in terms of lambda. So what are these design rules basically containing? Yeah, what information, what we have to follow, what kind of rules they are. So these rules are for minimum width, that is, you are drawing any pattern, so that pattern must have some minimum width. It can have more than that, but it cannot have less than that minimum width rule. Similarly, there are minimum spacing rule. Okay, that is, let us say I have metal 1 and metal 2 line, or maybe 2 metal 1 itself. So there is a minimum spacing rule which says that there must be some spacing, minimum spacing, yeah, as let us say. So that minimum spacing must be present in your layout between those two metal lines. Okay. There can be more than this as minimum. Okay, minimum spacing, there can be, the spacing can be more than the minimum spacing rule, but it cannot be less than the minimum spacing rule. Similarly, surround, there are rules for surround also. That is, within the metal, maybe let's say I have an active region here, that is source and drain diffusion region. Okay, the outer one is, this one is, the outer box is, let us say, my source and drain diffusion region, source region or maybe drain diffusion region. And then inside that source diffusion region, I have a metal line, and then this metal line and the source diffusion region are contacted by a contact. Normally contact is represented by a cross in the text, you will find. So there is surround rule which says that if some object is lying inside another object, so there must be some spacing here. There is a rule of spacing, that is, some spacing should be there, minimum spacing, and that minimum spacing should exist, right? It cannot be less than that minimum spacing. Similarly, I have surround rules for contact and metal also. Okay. So let us read this minimum width. It says this is the smallest dimension permitted for any object in the layout drawing. Okay, maybe let's say I am drawing a metal line, so I have a minimum width design rule. So that is, minimum width cannot be less than 2 lambda, for example. Okay, for metal 1. So this is minimum width rule. Spacing, that is, which is the smallest distance permitted between the edges of the two objects. That is, I have metal 1 as one object and another metal 1 as the second object. So I must have a minimum spacing between these two metal lines. Surround, this apply to objects placed within larger objects such as contacts. So I have a larger object, this one, okay, maybe source or drain diffusion region. Inside this I have a metal line, and then I have a contact which connects the metal line and the source and drain diffusion region. So there is spacing rule which says that the spacing between the edges of the outer object and the inner object. So there must be some minimum spacing between the edges of the outer object and the inner object. Then every layer, okay, last rule, every layer has minimum width and minimum spacing value, while surround values are specified as required. Okay, so that means every layer, I mean, this is a summary of all these three, that is, it should have minimum width and minimum spacing value, while also following some rules for minimum surround spacing values also. Okay, so what are these? We'll understand very soon, well, when we will draw the layout, and also when we will cover these layout design rules. Yeah, so for example, let us say we want to draw a N well, right? So these are the rules for N well. So all these rules, 4 rules for N well. And here you will find that there are 3 rules being specified. One is SCMOS, this one, first column. So this is scalable CMOS rule. Then you have sub-micron design rules and deep sub-micron design rules. Okay? So since we would be following this scalable CMOS rules, in fact these are better as CMOS, scalable CMOS rules, and Moses and Orbit Foundry also have specified these rules. So these rules are present in your tool also. So we'll use this column 1, while values of column 1. Am I audible?
Yes, sir.
Yes, sir.
Okay. So for example, I want to draw an N well. So rule number 1 says that my N well should have a minimum width of 10 lambda. This is in terms of lambda. All these rules are, that is dimensions are in terms of lambda. So minimum width of my N well should be 10 lambda or more. Just a second. Yeah. So minimum width of my N well should be 10 lambda, that is this 1.1. So let us say all these are N wells here. There are 3 N wells. So minimum width of N well should be, so this is my minimum width here. Yeah, width is this much. This is width of my N well. Okay. So the width of this N well should be 10 lambda. That is, this should be 10 lambda, this width. It can be more than 10 lambda, it can be 11 lambda, or maybe it can be also 20 lambda. Okay. Depending upon the size of the MOSFET, it can be more, but it cannot be less than 10 lambda. I mean, it cannot be 9 lambda. If you draw 9 lambda, it is a design rule violation. Okay. Similarly, rule 2 on N well says minimum spacing between wells at different potential. So it is possible that in your IC, these N wells, I mean, you may have 3-4 N wells, maybe more than that. So there is possibility that 2 wells are not at the same potential. Okay. So for example, these 2 wells, well number 1 here and well number 2. So these 2 wells are not at same potential, that is at different potential. So for the wells at different potential, there is a rule that spacing between these 2 wells should be at least 9 lambda. Okay. That is this rule here. Spacing between wells at different potential, maybe let's say this is at potential V1 and this is at potential V2. So these cells are different potential wells. So the spacing between these 2 wells should be minimum 9 lambda. It can be more than 9, that is 10, 11, 12, 20, 50, all allowed, but not less than 9 lambda. The 8 lambda, 7 lambda, they are not allowed. Similarly, maybe let's say this well is also at the same potential V2. Okay, that means these 2 wells are at the same potential. So I have another rule that is minimum spacing between wells at same potential. So that is equal to 6 lambda, right? So minimum well, this spacing should be minimum 6 lambda. It can be more than 6 lambda, but it cannot be less than 6 lambda. Okay. Similarly, another rule says minimum spacing between wells of different type. Okay. So I may have an N well also, and just a second, keep this here. So I may have an N well in my IC, and also I may have a P well. Okay. Now minimum spacing between wells of different type, that is these 2 are of different type, N well and P well. So minimum spacing can be 0. That is, these 2 wells can even touch each other. Right, so this is permitted. So this is 0 lambda. That is wells of different type. That is, these 2 wells can even touch each other. But others, I mean, it depends on rules. Yeah? You cannot touch the N wells together, but P well and N well touching is allowed. Then there are rules for minimum rules for active region also. So this green region is called active region. And this green region specifies your drain and source diffusion areas. So in your transistor, the green region will define your source and drain diffusion regions. Yeah. Okay. So yeah, so green region will define this active region, and it also has some minimum design rule. That is, let us say rule number 1 is that minimum width should be at least 3 lambda. Okay. That is, this minimum width, let us say this is width, this one. So this should be minimum 2 lambda. Mummy knows the password. Go. So yeah, so width should be less than minimum width should be 2 lambda. That means these two dimensions should be at least minimum 2 lambda. This one and this one, at least 2 lambda. It cannot be less than 2 lambda. Similarly, minimum spacing between the two actives, that should be also at least 3 lambda. That is, this is spacing. Yeah, we have two active regions here. Let's say this is one region and this is active region 2. So between these two regions, the minimum spacing should be at least 3 lambda. So this should also be 3 lambda. So what is lambda? Lambda depends upon the minimum feature size. So if I am using a 180 nanometer technology, right? So 2 lambda is L, okay? That is lambda is L by 2. So if I am working in a 180 nanometer technology, so lambda will be how much? Lambda is equal to L by 2. That is, lambda will be 90 nanometers. Okay. Then we have another rule, that is source or drain active to well edge. Okay. So this is you have two wells here, N well, okay, this N well. So source and drain active, that is this active which is acting as a source or drain diffusion region. So from this active to well edge, that is any of these well edge. So maybe this well edge is also existing here. So this should be minimum, this should be at least this well edge. It is wrong, I think, wrongly mentioned here. So this should be minimum 5 lambda. Okay, 5 lambda. So similarly, there are some other rules also between, active which is lying between two different wells. That is, one active is here, for example, lying in this P plus select region, and the other active is lying in this N plus select region, right? N select region and P plus select regions. The two actives are lying in these two regions. So I must have some minimum spacing, and that spacing is 3 lambda plus 3 lambda. That is 6 lambda, okay? This much. So similarly, there are rules for other components also. For example, poly. So we understand poly here means the polysilicon line, or which is used for the gate. Yeah, poly always refer to gate here. In fact, poly lines are also used to connect the two gates of the two MOSFET. Okay. For short wiring or short routing, these poly lines can be used. In fact, let us talk something more about this polysilicon. I'll take this white screen. Now in a MOSFET, we understand that let us say we have a N-type MOSFET, N-channel MOSFET. So I have two N plus regions which define my source and drain. Okay. And substrate is obviously P substrate, let us say. So plus here means it is heavily doped. Yeah? These two regions are assigned this plus sign. So plus means it is heavily doped. If I don't use plus, so that means it is lightly doped. And source region and drain regions are generally in a MOSFET heavily doped, right? It is never lightly doped. It is always heavily doped. Okay. Then on these two regions, I'll have a silicon dioxide also, let us say. And then on silicon dioxide, I have a poly, or what we call as polysilicon gate, right? So I say that in short, it is poly. And this is my silicon dioxide if. Okay. This is my NMOS structure. It looks like this. Now this poly or polysilicon is actually the same silicon which is used here in the substrate, right? So here in the substrate we normally use crystalline silicon. Okay, so the wafer is always crystalline wafer. So what is crystalline means? So crystalline means the atoms in the lattice of the silicon material, so they have a periodic arrangement. Okay. So for example, these atoms here, they seem to be periodically arranged. Okay. And let us say that this is silicon lattice. So all these atoms are periodically arranged. So when this situation happens, so we say that my semiconductor is a crystalline semiconductor, right? So crystalline here means that the silicon atoms are let's say if it is a crystalline silicon, so that means all the silicon atoms are periodically arranged. Of course, it's a a cubical lattice. So in that cubical lattice also, all these atoms are arranged in a periodical fashion or periodical manner, right? So some periodical arrangement of the atoms is present. We say that the structure is crystalline. Okay? Now, what is polycrystalline? Right. So as I said that we don't have any separate material called poly or polysilicon. It is the same material silicon, okay, but it is called polycrystal. Why? So because you see that silicon dioxide here, right? So this is not in solid form. So this is in amorphous state, or maybe you can say that it is not in solid state, amorphous or gaseous state. Now on this amorphous silicon dioxide, you deposit silicon. Okay, not polysilicon. There is no material in this world called polysilicon. So you're depositing crystalline silicon on this amorphous silicon dioxide base. So what will happen if you deposit something on a not on a solid surface, right? I'm trying to deposit something on a solid surface. So what will happen is whatever I am depositing, that will not maintain its crystallinity. That is the atoms of the material which I am depositing here. That is silicon atoms. So they will try to move from their positions. Why? Because the base is not solid, base is amorphous. Okay? So when they do that, so let us say that let us take it here. So atoms are now, the periodic arrangement of the atoms is now completely disturbed. Okay? So now we don't have a periodic arrangement of atoms. So what we may have, maybe the atoms have moved now because the base is not solid. So I may see some sort of regions which have periodicity, but those periodicity are localized now. Okay? The entire lattice is not a periodic. So for example, this portion of the lattice looks to have a periodic arrangement of atoms. So similarly, this portion of the lattice, silicon lattice, seems to have a periodic arrangement. Similarly, this also seems to have a periodic arrangement. Okay, but the entire lattice does not have same periodic arrangement. Okay, so you have small regions of crystallinity. Okay, so this kind of a semiconductor or a material is called a polycrystalline material. That is, the complete crystallinity is not present. That is, the entire silicon or entire lattice is not periodically arranged. The atoms in the entire lattice are not periodically arranged, but what we have is we have small regions of periodic arrangement of atoms. That is, small regions of crystallinity are present. So this is called a polycrystalline structure. Yeah, so that was called actually a polycrystalline structure. I'll take that screen again. Okay. So that was called polycrystalline structure, where you do not have the complete periodicity, but you have separate regions, small regions, which may have some sort of crystallinity. Okay. So for example, here, all these regions, they may have some sort of crystallinity, but the entire lattice is not having a periodic arrangement of atoms. So this is called polycrystalline silicon, or polycrystalline arrangement of atoms in material. Okay. So in a MOSFET, as I said, that we do not have any material so called as poly, but the process itself defines the gate to be called as polysilicon gate, because you're trying to deposit the same crystalline silicon over this amorphous silicon dioxide, and because of this amorphous state of silicon dioxide, the atoms of the crystalline silicon cannot maintain their periodic arrangement and they try to move, and we have a region of a periodic arrangement of atoms, small region. So this structure is called polycrystalline. So we have polysilicon. Now other question would be that whether this silicon or polysilicon which is present at the gate is doped or not, right? So we understand that to have a conductivity from any material, it should be doped either into N type or P type, yeah? Because otherwise it would be an intrinsic semiconductor, right? So to increase the conductivity or to make it useful for conducting current, you need to either dope it with p-type or n-type impurity. That is, you need to either incorporate majority carriers as holes in a p-type or majority carriers as electrons in a n-type semiconductor. So the question is whether this polysilicon is doped or not. Yeah, because this is also a semiconductor. So whether it is doped or not. So answer is yes, obviously it should be doped, otherwise the conductivity would be very less or maybe zero. So how it is doped is when you are creating these two regions, right? Drain and source diffusion regions. Okay. So you are exposing this entire wafer to ion beam. Okay. So by ion beam implantation, let us say we are trying to dope these source and drain diffusion regions by using ion beam. So during this ion beam implantation, that is, these diffusion regions are created when this silicon dioxide, this polysilicon. So this is also doped by the same impurity. Okay. We had this polysilicon gate over here, and we are trying to dope, or we are trying to create diffusion regions, source and drain diffusion regions. Okay. So during the same time, this polysilicon also get doped. What kind of doping that means? So if I am making an N-type MOSFET, the polysilicon will be doped with N-type impurity. That is, it is now N-type polysilicon. So if I am having a P-type MOSFET, let us say, so polysilicon will be doped with what type? It will be P-type dope. Okay. Now let us come on to this polysilicon design rules. So this polysilicon design rule says, number one, it says that minimum width of the polysilicon should be at least 2 lambda. It cannot be less than 2 lambda. So here you will see that these are two polysilicon wires. Okay. Here also polysilicon wire is present, but these two cases are different because these two polysilicon wires are crossing this active region. Right? So there is another rule for having a polysilicon wire over the active region. What should be the minimum width, and when it is not in the active region, then what should be the minimum width. So considering that the polysilicon is over this active region, right? That is, whenever the polysilicon crosses this green layer active, so always, whenever it crosses, as soon as it crosses, a transistor is formed. Okay, for example, here I have two transistors. Okay, two gates are there. These two polysilicon, right? And the drains or source of these two MOSFETs are maybe shorted. So the design rule says that minimum width of the polysilicon should be 2 lambda if it is crossing the active region. So this 2 lambda actually specifies the gate length also. Okay. 2 lambda is the channel length. So that means the channel length, that is this width, this is 2 lambda, and this is also equal to the channel length of the MOSFET. And whenever it is crossing the active, then it is fixed to 2 lambda. It cannot be more than 2 lambda also, right? So you have to keep it 2 lambda only because it is specifying the channel length or the gate length of the transistor. Now, when it has completely crossed the active region, you can increase the size of this. Okay, but you cannot increase the size here, or you cannot also reduce the size here. But here, you can increase the size. So it can be more than 2 lambda. Maybe you want to connect, for example, this poly gate to some other gate. Okay. So maybe for that purpose, you need a contact also. Or maybe you want to connect this poly line to a metal line for getting the inputs. So you need to have a contact also. So contact, the same square box. So that is called contact. So maybe let us say, let me take a metal line over here. So I say that this polysilicon has to be connected to this metal line. Okay, they are overlapping now, metal line. Let's say this is my metal one and this is poly obviously. So I need to connect them. So I'll drill a hole in between them, maybe here, let us say. And then in that hole, I'll fill this contact material. So contact are represented by cross. So I have a contact over here between metal one and poly. So for having a contact, because contact size is also 2 lambda by 2 lambda. Yeah? Minimum size of a contact is 2 lambda by 2 lambda. So if the poly size is 2 lambda, then it will be difficult to make a contact, because then the surround rule will also come into picture. That will say that you must have some minimum spacing between the edges of this metal or maybe the poly to the contacts. So those surround rules will also come into picture. That is why one has to increase the dimension of poly here. Okay. So then we have another rule which is called minimum spacing over a field and minimum spacing over an active. So many rules are there. Okay. So for example, this rule, that is how much poly should be at least, the edges of this polysilicon and the active. So how much spacing should be there? So that should be somewhere around 2 lambda, right? So it cannot be less than 3 lambda. Sorry, 2 lambda. Okay. So similarly, there are some more rules for defining your P plus or N plus select region. Okay. So for P plus and N plus select region, I have, for example, a rule that the P select, the boundary of P select and the boundary of the polysilicon. So there must be some minimum spacing. So that minimum spacing is how much? 3 lambda. Okay. So this should be 3 lambda. Similarly, if there are contacts, that is, if you have a connection between P select region and this is the bottom one is N select region. So again the spacing between, that is surround rule comes into picture here. Spacing between the edge of the outer material, that is P select, and the inner material, that is contact. So that should be at least 1 lambda. 1 lambda.
Hello, sir.
Yeah,
Hello.
please.
Sorry to interrupt. Sir, do we have to draw the layout because there are too many rules? So, are we supposed to draw the layout?
Yes, we have to learn this course. I mean, it is a part of this course. So in fact, we also have a MOU with SCL Mohali, Semiconductor Complex Limited, which is the only fab lab in India. So maybe in your thesis, you can create some IC, some novel structure integrated circuit you can create, and then you can send it for fabrication. It would be a very good thesis. In fact, many of the students have done this in past. So it is a part of our course. You will have to learn this, both embedded system design and VLSI design students.
Okay, so in PCB designing, usually we use softwares wherein they already have the rules in the software, and then we do a DRC check and other things by which we verify.
Yeah,
so in this, do we have any software which already have some rules?
Same thing exists here also. Design rule check you will perform here also. The rules are already there. You have to select those rules, okay, from the foundry, whatever foundry you are considering. So you will select their rules and start drawing the layout, and then perform a DRC or design rule checker. Okay, and then if there are errors, you have to clear those errors. So all those things which you used to do in PCB, here also you will do the same thing. And the software that we have in our lab, we have very good commercial softwares, which are having very high cost, and they are used in industry for these purposes. So we have Cadence, we have Mentor, we have Synopsys, right? So all these three tools are the top frontier leading tools in the industry. And for this course purpose, I will share with you the student version of one of the layout editors. All layout editors are more or less same, similar. So since the lab is not accessible to you, currently the lab is not accessible to you, so obviously you'll not stop your learning process. So learning process should keep on going. So how it will be on? So I'll just share a student version copy of one of the softwares, and all softwares, all layout design softwares are similar. Yeah, please.
Okay, thank you, sir. Thank you.
Okay. Yeah, so you have to be very serious in this. You have to learn all these things. Okay. You don't have to learn the layout design rules. I mean, always whenever you will draw the layout, these rules will be with you. You will take a printout of these rules, maybe 2-3 sheets. You will take the entire rules, and as you become expert in drawing the layouts, you will not refer to these rules. I think later on, after maybe an experience of 2-3 layouts, you will not even refer these layout design rules. You will be So once you become an expert, so these layout design rules you will not even want to keep with you. Anyhow, so let us talk about these rules. So then we also have a rule for this spacing between the active region, that is green region, and this N plus select region. Right. So all these dimensions have to be carefully selected while drawing the layout. Okay. So the spacing can be more, but it cannot be less than the already specified. Okay. So when somebody wants to optimize the performance, that is somebody has a very stringent performance metrics that has to be met, then obviously one has to play with these design rules. That is, one has to tweak these dimensions and make all those dimensions minimum. Yeah, I mean, if possible, if these dimensions can be kept minimum, then obviously the size of the layout can be small, and obviously then the size of your IC, that is wafer that is being utilized for fabricating IC, would be small. So you will save some money of the company also. Okay, and also your design performance metrics, so they depend upon the parasitics that are present in the actual fabricated version of your chip. So those parasitics depend upon your layouts, right? So the bigger your layout is, the more will be the parasitics, and more it will affect the performance. So you have to, designer has to always, optimize their layout so as to meet these minimum, width rules or minimum spacing rule or minimum surrounding rules, right? So obviously you have an option of keeping things bigger, but then bigger things come at some cost. Okay. Then similarly, we have a rule for contact to poly and contact to active region, right? So for example, here I have a contact in the active region. So the dimension of this contact is 2 lambda by 2 lambda. So this is very important to understand that the contacts, for example, this 5.1, this contact, poly contact, or maybe active contact, these are exact in size. Okay? There is no maximum rule or minimum rule. In fact, the contact should be exact of this size, that is 2 lambda by 2 lambda. It cannot be less than 2 lambda, it cannot be more than 2 lambda. Other structures you might have seen that they can be more than the minimum specified, but only this contact, this cannot be more than the minimum specified. So if it is 2 lambda by 2 lambda, it has to be 2 lambda by 2 lambda. It cannot be less, it cannot be more. Others can be more and less, but this contact and also the poly crossing the active region. So these would be only of the same exact dimension. It cannot be more, it cannot be less. Okay, please turn off your mic, please. Then another rule says minimum poly overlap. Okay, 5.2 here. So this rule 5.2, it says minimum poly overlap, that is the contact is now placed inside this poly. Okay, contact is placed, this contact is placed inside this poly region. So I have some minimum spacing rule, that is the edge of this poly should be at least this much space away, that is 1.5 lambda. This is 1.5 lambda, right? Then similarly, minimum contact spacing, that is the spacing between, minimum spacing between two contacts, it should be around 2 lambda. Okay. Similarly, about active contacts, the size of the active contact should be 2 lambda by 2 lambda again. It is fixed 2 lambda by 2 lambda for this contact. Then minimum active overlap, that is I think active overlap should be similar to this one. So you have some spacing over here left and some spacing here left. So that should have should be somewhere around 1.5 lambda. Okay. Similarly, contact to poly spacing, 6.4 here. So contact, this contact to poly spacing, and this contact is lying in the active region. So this should be again 2 lambda minimum. Can be more, but it cannot be less than 2 lambda. Now, similarly, I think these are, this one is the last set of why also is there. So for metal 1, I have a rule that the minimum width of the metal 1 line should be at least minimum 3 lambda. Okay. That is this width. Okay. Here, this is metal 1, the blue one is metal 1. So the width of this metal line should be minimum 2 lambda. Okay. So this should be minimum 2 lambda. So that also applies that this, here it is 2 lambda. Okay. Then minimum spacing. So that should also be equal to 2 lambda. Okay, so minimum spacing means this is another metal or maybe metal 1 only, this purple one. Okay. It is looking purple because of this poly which is overlapping this blue line metal, right? So blue line here metal and poly red line. So they both are overlapping. So poly is now bigger. So this is now poly here, red one. Okay, and this is overlapping the blue line, so that is why it's looking purple, right? So the spacing between the metal 1 and metal 2, that is this is spacing, this is metal 1 and metal 2, so that should be minimum 2 lambda. Yeah, so then there are some more rules. For example, minimum overlap of any contact, that is this spacing. So this should be somewhere around 1 lambda. So all these spacings, that is from here to here, here, this one. So all this should be minimum 1 lambda. It can be more, but cannot be less than 1 lambda. Similarly, we talk about via now, via contacts. In fact, let us also talk about via contacts. So let us talk about this via contacts. So what are they? So let me take again that white screen. Okay. So suppose I have let's say 3-layer process, 3 metal layer process, 3 metal layer process. So today in the IC design process, you will find that more than 11 layers are used. More than 11 metal layers are used. So let's say I have a 3 metal layer process, 1 metal, 2 metal, and 3 metal. Let's say M1, M2, metal 2, and metal 3. And in between these two metal lines, all these metal lines, you have some insulation, and that insulation is silicon dioxide insulation, right? So I say that I have an insulation between these metal lines, and that insulator is normally silicon dioxide, which is deposited by plasma enhanced CVD. Yeah? We understood that this is deposited using plasma enhanced low temperature CVD process. Okay, so silicon dioxide in between metal 1 and metal 2. Now the question is how we will connect. If I want to have a connection between metal 1 and metal 2, how it is done? So for providing a connection between metal 1 and metal 2, in the actual manufacturing process, what is done is, a hole is drilled from metal 1 to metal 2 via the silicon dioxide, right? So a hole is drilled here, and then that hole is filled with another metal. So that metal could be platinum or maybe tungsten. So platinum or tungsten can be filled here in this hole, right? So a hole is drilled between M1 and M2 via the silicon dioxide. So I have a hole here now, cavity, and that cavity is filled by platinum or tungsten. Okay, and this type of connection or contact is called a via contact. That is, you are connecting two metal layers, okay, of different type via contact, which is called a via contact. So this via contact also has some rules. So let us talk about those rules. So this via contact has rules. What are those rules? Exact size of via. So that should be at least 2 lambda by 2 lambda. So for example, I have a via here. These two vias are here. And the exact size of this via is 2 lambda by 2 lambda, all dimensions. Then the spacing between two wires, minimum spacing. So rule says that minimum spacing should be at least 3 lambda. So I have 3 lambda spacing between two wires. Similarly, I have few more rules, that is surround rules for this wire. So surround rule says that from via edge to active edge, I must have at least 2 lambda spacing. Similarly, surround rules for when active is or metal is outside this active. Via and metal are outside outside this active region. In this case, via and metal both are inside the active region, but in this case, via and metal both are outside the active region. So I have another rule. In fact, the dimensions are so the same in that rule, 2 lambda in both the situation. That is, this situation also 2 lambda, and this situation also it is 2 lambda. Okay. So I think we are done with the layout design rules, and yeah, maybe this is the last rule. Yeah, this one is the last. So it says that for metal 2, yeah, that was for metal 1. So for metal 2, in fact, for all layers you will find there are some rules. So metal 2 has a rule for minimum width. That is, minimum width of metal 2 cannot be less than 3 lambda. That is, this spacing, this should be at least minimum. Sorry, the width of this metal 2 should be at least 3 lambda, right? The minimum spacing rule. So that also says that minimum spacing between metal 1 and two metal 2 lines. So these are two metal 2 lines, and minimum spacing between two metal 2 lines should also be equal to minimum 3 lambda. It can be more, it cannot be less than that. Okay. Similarly, minimum overlap of via 1. Okay. So I have a via 1 over here contact. So via 1 edge is here. So the overlap, that is spacing between this region, right? So that should be at least minimum 1 lambda, right? Yeah, so these are the rules for metal 2. So all layers which you are drawing in the layout, so they have some set of rules. So one has to follow those rules. Designer has to follow those rules for if the industry has to, or the foundry has to fabricate your IC, then you'll have to follow these rules. So in fact, these layout design rules are basically a contract between a designer and the foundry. The foundry says if the designer follows these rules, then only the chip or IC can be fabricated for the designer. Okay. I think somebody is trying to connect. Let me see who is it. Okay. Yeah. Now, having a knowledge of these rules, now we are in a position to understand and draw the layout of our IC. Okay. So let us, after here, let us now try to understand this NMOS layout, right? That is, this is the transistor, NMOS transistors layout. So in this NMOS transistor, how to draw the layout of NMOS transistor. So first thing is, you need to understand that the background, that is this background, the white one, which has grids, these small dots. So this background is, first thing is that this background is a p-type background always. Okay. And in fact, today the wafers that are being produced, so that those wafers are also p-type, and this can be ensured by putting a p-type impurity in that Czochralski process. We had the molten silicon in that crucible. So in that molten silicon crucible, you put some p-type impurity. Okay, so that the cylinder which is, or I naught which is created, so that is completely p-type. So p-type wafers can be produced that way. So let us say that my background of this layout editor tool is p-type. That is, I have a p-type semiconductor in the background. Now NMOS can be produced by first step to produce NMOS is that you deposit this N select. You draw a region where you will define your NMOS. Yeah. So that region is, let us say this entire outer one, yeah, outer box. So this represents N select. Okay. Now this this box that is N select. So this also has some minimum design rule, that is this width should be having some minimum value, maybe 10 lambda or 20 lambda. So that has to be followed. Yeah. So first thing is you draw N select, that is the region where you will define your MOSFET. Then second point is you need to draw this active, that is green layer. So this active will define your source and drain region, that is N-type source and drain diffusion region. Source and drain diffusion region will be identified by this active. Right? So first thing is N select, second thing is active, and third, you draw this polysilicon line. Okay. So you cross your gate or polysilicon line over this active region. So normally, if you want symmetrical source and drain contact, so you will normally pass this poly line in the center of this active region, so that source and drain contact regions are of the same size. So capacitances associated with these two regions are also same. Okay. So these are called symmetrical MOSFET. So for a symmetrical MOSFET, you will always pass the poly line or gate line through the center of this green or active region. Then in this active region, you want to connect the active region to this N select region, right? So for this, you will again make a box of this blue line, which is metal. So this is third step, metal. Okay. Then you want to connect this metal and then green line and this N select, all three layers. It's a layered process. So first layer is this one, second layer is this one, and third layer is your blue line or metal. So you want to connect them. You provide a contact here. This is my contact. So the entire, this one is, black one is a contact. You put a contact in the center. So again, the dimension of this contact should be 2 lambda by 2 lambda. And the spacing from, this is spacing, this should be minimum 1 lambda. All edges, this one, so all should be minimum 1 lambda, right? So the contact is process number 4. So once you do this, these 4 steps, your transistor is now created. And you will also see here that you have an extra, arrangement over here, and this is for connecting the body. Okay, the body of the NMOS is connected to the most negative supply in the circuit. Okay, so in a NMOS, you normally connect the body to so the body you have to connect. In fact, you want to make the diodes in your the parasitic diodes. Maybe let us take another screen. So I have an NMOS here, for example. So in NMOS, I have 2 regions, N plus, source and drain, and P-type substrate is there. Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
So in NMOS, I have 2 regions, drain and source, N plus source and drain diffusion regions. Okay. Now in between this N and P regions, you will find that this represents actually a parasitic diode, right? So we don't want this diode to be present there, but the process itself defines the origin of these parasitic diodes, right? So I have these parasitic elements or diodes present in my NMOS. Similarly, in my PMOS also I have these parasitic diodes. Okay? So we don't want them, but they are always present. Okay? Because the process itself defines the origin of these parasitic elements. Okay. Okay. So we don't want these parasitic elements to conduct. We don't want these diodes to be switched on. So always in your IC design, the MOSFETs, in the MOSFETs, these parasitic elements will always be kept reverse bias so that they don't become on. So for making it reverse bias, so obviously you want to connect the P-type body to ground or most negative supply. Okay, so then only this diode can be reverse biased. Okay. Similarly, I want to reverse bias this parasitic diode because I don't want to keep them on, so that's why I'm reverse biasing it. So I want to keep this reverse bias, so I have to connect the body to the most positive supply. Okay, plus VDD. In PMOS, you connect it to plus VDD, and in NMOS, you connect it to in PMOS, you have an N substrate here, right? So in PMOS, you connect it to plus VDD body, and NMOS, you connect it to ground. So same body contact. In fact, if you don't connect this, you will see that there is an effect called a body effect where the threshold voltage of this device can vary. If this device, that is parasitic element, switches on, then you'll have a direct connection between drain and the body. So you'll have a conduction going on between substrate and the source and drain. So it can affect the threshold voltage of this MOSFET. To avoid this, these have to be always reverse biased. Okay. So now to provide those body contacts, we have another set of arrangement just beside this NMOS layout. So this is for providing the body contact. So how it is provided? In the same P-type substrate, right? So background was, remember, P-type. Yeah? So this background. So this is was P-type. So in this P-type region, again you collect, you create a heavily doped P-type region. So that is P select. This region is actually P plus. P select whenever I say, so that is P plus or heavily doped P-type region in P-type again. Okay, and then you again make a active over here, and then similarly you, active always. Whenever you say you draw an active line over here, so that means the entire active region, that is green region, this has either P-type or N-type impurity. Okay. Only this region has P-type diffusion or N-type diffusion. Outside it is not P-type or N-type diffusion. So similarly for a MOSFET here, this entire region is this is N-type, so it is N-type. Entire this green region, source and drain diffusion. Okay. Now the width of the MOSFET, if somebody asks me what is the width of the MOSFET, I'll say that the width of the active is actually the width of the MOSFET. So this is the width of my MOSFET. Channel length, that is this one. So this is my length of the MOSFET. So W by L ratio comes from this W and L from here. Okay. So once I do this, I will now connect this to ground. Okay. Since I want to keep the parasitic diodes in reverse bias. So I'll connect this to ground. So if I do this, so that means I have provided a bulk or body contact. Okay. Similarly, for PMOS also you will have a bulk or PMOS contact. Bulk contact. Now for PMOS, again we start with the same concept, that is the background is P-type. Okay. So in a P-type material, if I want to create a PMOS, so I would need an N-well. So number one is that you need an N-well. So this entire box, the outer box. So this is my N-well. So number one is you draw N-well for PMOS. Okay, number one. Then inside that N-well, you will need to draw this P-select. Okay, this is process number 2. P-select, because drain and source would be PP plus type. Then third is active. That is, you define your P plus and P plus regions, source and drain regions. Right. So this is my width of my PMOS. Okay. So PMOS width is this, not this. So this is not the width. Okay. This is not width. So width is only defined by the active region. Okay. Third is active. Then fourth is metal, blue one. Fifth is contact. Or maybe you can say fourth is this one. Let's say 4 dash. 4 could be this one, and then you draw this metal contact and then contact over this metal line, right? Then these two things can be connected to other MOSFET, that is source and drain of this PMOS can be connected to other MOSFET, or maybe power or ground lines. Now to provide a body contact to this PMOS, you define a heavily doped N-type region in the N-well. So inside the N-well, that is maybe let us again come on to this CMOS, where you have an N-well here, and in N-well you have P plus regions. Okay, let's say these are my P plus regions in N-well. So this is N-well. So you need to connect this N-well to for connecting this N-well, you again create a body contact over here. Let us say this is body contact, and connect this body contact to the most positive supply. So maybe if the most positive supply is present at the source, so you connect this to source body. Okay. So similarly, the body contact is created, and then this body contact is extended here and connected to VDD. So this is connected to VDD. This is extended. Okay. So normally VDD lines are running, on top of the layout here. For example, here on top of the layout, your VDD will be running. So always try to follow the same thing, that is VDD lines will always run on top, and ground lines will always run at the bottom of the layout. So in real or actual IC design process also, we follow the same thing, that is power and ground lines will be running on top and bottom. Similarly, clock signal will also be running on the top. Okay. So this is how a PMOS layout can be created. Now, if somebody wants to, create an inverter using these PMOS and NMOS, so what we have to do is, we have to simply copy both PMOS and NMOS in the same, layout editor window, and then provide connection between the drains of the two MOSFETs, and also connect the gate of the two MOSFET. Okay. So if I can do this, then I will create a CMOS inverter. So maybe let us see. Let's see here. Maybe let us say we have created a PMOS and NMOS, right? So this top is PMOS, this structure is PMOS, and this is NMOS. So I have copied the same PMOS and NMOS, which I have drawn into this layout editor window. Now, these two gates are connected, so that means here I can apply input. So input can be applied here because the gates are shorted. Poly represents a gate, so both the MOSFETs have the gates here, so these two gates can be connected via the poly itself. Then an input can be provided through this poly. Then what we will do, let's say this is my source of this MOSFET, so source is connected to VDD. So this is VDD. And also the body contact is connected to VDD. The body contact is also connected to VDD. Similarly, the source of this NMOS, so this is connected to ground. So ground line is running at the bottom. So I connect source to the ground. and also the body contact to the ground. And then I am left with the drains of the two MOSFET. Okay. So in the CMOS inverter, the drains of the two MOSFET are shorted. Okay, here, the two drains are shorted. So let us short this two drains. Okay. So let us extend this blue line, that is the metal one line over here. And then I have a connection between the two drains, and here I can take my output. So my CMOS inverter is created. Okay. So maybe I'll show you the complete finished version. Yeah, so this is my CMOS inverter now. This is VDD and this is ground. So next process is that we need to learn how to draw this layout and how to draw the layout of CMOS inverter. And why we would learn this is because we want to extract the parasitics from this layout. Yeah, obviously, depending upon how you draw the layout, okay, how optimum is your layout, the parasitics can also be optimized. That is, parasitics means R, L, and C. So all these R, L, C we will try to extract from the layout, and then we will include these parasitics in our SPICE simulation. So we had done SPICE simulation in assignment number 1 and 2, and that was for also inverter, the same inverter. Same inverter, we will try to draw the layout of the same inverter, extract these RLC parameters, and put these RLC parameters into assignment number 1. And then again perform the simulation. And then we will try to figure out the differences between the SPICE circuit simulation without these RLC parameters and with these RLC parameters. Obviously, you will see some change between the performance of your CMOS inverter when you include this parasitics and when you don't include these parasitics. And these parasitics will go up. I mean, these will vary with the size of your layout, right? So this depends upon the size of your layout. So layout size, these parasitics depend. So that means one has to always think about optimizing the size of the layout. Okay, so that is actually the purpose of a design engineer, a layout design engineer who is working at the back end. So the purpose is to optimize the layout area, that is, size of the layout has to be optimized so that these RLC parameters associated with the layout can be optimized so that the performance of this circuit can be optimized. So maybe, maybe I think we can learn this layout design process in the next lecture.
Sir?
Okay. Yeah, please.
Sir, why we connect the V out in this way? I can't understand the V out connection.
I mean, it's all up to you how you want to connect. You don't want to connect this way. You can simply take output here.
Okay, that's my
Don't
confusion.
need to connect this way. Don't need to connect this way.
Okay.
So if you want to take an output here, you can simply take output here.
Okay.
Don't need to connect this way. Yeah.
Okay, sir. Thank you.
Yeah. So if you have any questions, then maybe you can ask. And I think that the demo of that layout editor tool and the extraction of this parasitic element, this requires another, I think, 1 hour at least. So maybe on Tuesday, I think we have a class, so we can learn the process of drawing the layout and then extracting the parasitics from them later on Tuesday. Okay. So I think we should end the class now. And if you have any queries, then you can ask.
Sir,
Yes.
sir, we'll be doing this layout extraction on a software tool.
Yes. So I'll share one software with you. So you will draw the layout there, and that software has an option of extracting the parasitics from the layout. The same software has the option of extracting the parasitics, and those parasitics which you extracted from the layout, so those parasitics you will use in your SPICE simulations.
And all these rules we have to learn by
Yeah,
heart.
you need to learn. So you need to become good IC designer. You want to find a job in this field, right? So obviously you need to learn these tools because companies expect, industry expects, a full working knowledge on at least these tools, right? So obviously, if you want to get good job, you will have to train yourself according to the industrial needs.
And sir, as far as our syllabus is
Sir?
concerned, this part is not mentioned there. So,
No, it is there. Maybe just one or two line, or maybe one keyword might have been mentioned over there in the syllabus. Okay, so it is there in the syllabus. In fact, it is one of the most important part of your syllabus, digital IC design. So whenever somebody is talking about integrated circuit design, one cannot say that you will not learn layout designing, because it's a major step, major important part of your IC design.
okay, sir.
Yeah. So don't restrict yourself from learning this tool, or maybe this part of this IC design, because this is one of the most important part. And many of the companies in India also are working on and offering jobs on this backend part, that is layout design. So apart from front end design, there are job openings for layout designers also. And layout designing job will earn you a very good amount. Companies normally pay a very huge money to layout design engineers, because everybody cannot draw the layout, right? So one has to be an expert, one has to have an understanding, one has to have a knowledge on this. Then only one can be a successful designer. So industry is looking for successful designers, good designers. Yeah?
So
It's an- yeah.
can you lecture set or any tutorial for it,
Tutorial
for understanding this software?
well, I think I will cover everything in my demo, the demo that I will give you. So that will cover everything. And apart from this, if you want to know how to design the layouts and the
Yes, sir. That's why
techniques in layout design, so there is a very good book, and I had referred that earlier also in my first lecture.
Oh,
The book,
what's okay.
yeah, Principles of CMOS VLSI Design by I think Neil and Weste, Kamran Ishragin and Neil Weste.
Okay.
So I had referred that book to you as a reference book, and it had talked about the layouts in detail. So it is the best book for layout. You don't need any other tutorial. But yes, for working on tool, I mean the knowledge of tool, I'll tell you how to proceed with this layout design process on that tool.
Okay, sir. Thank
Yeah.
you.
Yeah. Anything else? Yeah, so Ankit, I think you have asked that whether these rules are same in all types of fabrication software. So all type of softwares have same rules, Cadence Mentors or whatever Synopsys. So all these layout design tools have same rules. Yeah, anything else? If you have any other query, then please ask. Otherwise, let us end the meeting. Okay, so I am disconnecting, right? The class is ended now.